So to finish up what we were saying about mass spectrometers, this is how I have commonly seen mass spectrometers in use. This is referred to as a high-performance liquid chromatography column. So liquid chromatography is going to separate on the basis of polarity molecules from one another. The most polar molecules come out first. The least polar molecules are retained in the column and come out more slowly. But each of those molecules are in turn subjected to the mass spectrometer. So we get a particular molecule out here, small at first, very polar. It passes through this device, separating into molecular ions. We get a fingerprint for that particular molecule. We wait a little while longer, a larger molecule comes out. It is broken up into many fragments. Its molecular fingerprint can now be detected. And then we wait still longer, and very large molecules are finally going to pass through here. And there's a particular molecular weight that pharmaceutical chemists are interested in, because if a drug is too large, your body will start destroying it right away. If it's too small, it may be passed out through your kidneys and in your urine. So they're looking for this sweet spot of molecular weight for a potential drug. At this stage, we can actually start to sort out candidates for potential development into therapies. So what's happening here then is we're getting longer and longer retention times in this direction, so stuff that's coming out of our column more slowly. But then along this axis, we're getting that mass to charge ratio that we see associated with our spectrophotometer, mass spectrophotometer. And so we're getting the fingerprint for each molecule, depending on how polar that molecule might be. So we will get into chromatography a bit later in our course, but the mass spec is that molecular fingerprint that's so useful to analytical chemists or those who are looking for potential drugs. Just a quick aside here, these are drug candidates that are still in the process of undergoing phase 2 and 3 trials. Phase 3 means that humans are actually being subjected to these things. Phase 2 means that animals are being subjected to these things to see how toxic they might be. Tetrodotoxin, coming from, well, this is actually not tetrodotoxin. This is a slightly different substance, but tetrodotoxin is something that our textbook actually mentions. And so we'll go there. So tetrodotoxin was a candidate for nerve pain as a therapy. When we go to deal with molecules that are this complicated, we might be asked its percent composition or its molar mass, and in fact, we have to do the molar mass before we can get the percent composition. When we refer to percent composition, we are asking what is the mass of each element relative to the entire mass of our compound. In other words, what percentage of the mass of this compound is carbon, what percentage is hydrogen, what percentage is nitrogen, what percentage is oxygen. Now, this is percent by mass. If we were looking at percentage by atomic number of atoms, then obviously hydrogen is the most abundant, carbon next, oxygen, then finally nitrogen. But in fact, it's always with respect to the mass when we say percent composition. Now, to do that, I like to organize my work. I set up a table. Element, atomic weight, atoms per formula, contribution. Now, these, if we were to draw these out by hand, they would get a little more complicated looking. I'd have 11 atoms of carbon per molecule of C3H17N3O8. And this would have the units of grams of carbon per mole of carbon. So in fact, when our units work out this way, this is the grams of carbon per mole of molecule. This is the grams of hydrogen per mole of that molecule. Likewise. These are all good to 4 sig figs. These are the 4 sig figs. But notice that I've written them out entirely. Because this is only good to 4 sig figs, I have to chop off here 1 digit after the decimal point. This would allow 2 digits. This would allow 2 digits. And this would allow 1 digit after the decimal point. Well, I always go to the least number of digits after the decimal point. And so my answer, correctly rounded, and I've actually made an error here, correctly rounded is 319.5 grams per mole. Oh, because I can only have one digit after the decimal point in the sum of these things. Now, what about percentage? I'm going to take this number, I'm going to divide by this number, and then multiply times 100. This number divided by this number times 100, this divided by this divided by this. When I complete that, I find that tetrodotoxin is 41% carbon, about 5% hydrogen, 13% nitrogen, and about 40% oxygen, despite the fact that oxygen is present 8 times, much less than carbon. They are roughly contributing the same to the percentage of the total mass of that substance. Now, here's where things get tricky. You've done molar mass calculations before. We did that for hydrogen peroxide way back when. You're doing it in an experimentally derived way when we look at the molar mass of an acid. But here, our textbook uses combustion as a way of analyzing a sample to determine its empirical formula. We say empirical, we mean derived by experiment. And here's the experiment. I'm going to take my sample, I'm going to heat it to a very high temperature. I'm going to then add a bunch of oxygen, and now my sample is going to undergo combustion. At a particular pressure of oxygen, depending on our sample, anything will burn. If you get the concentration of oxygen high enough and the temperature high enough, anything and everything will burn. Got to be careful about that. Our sample is then passed through first an absorber of water. This is magnesium perchlorate. And so water gets absorbed here, and we can very accurately measure how much water is absorbed by our magnesium perchlorate to very high precision. We then have a material that can absorb carbon dioxide. That material is sodium hydroxide. We are literally converting carbon dioxide from our sample into baking soda. And that increase in mass we interpret as carbon dioxide being fixed at that point. Oxygen, other gases like nitrogen dioxide, which is common to these kind of problems, simply pass on through. So we need to know the mass of our sample. We will never be given the mass of oxygen that's actually combined with our sample. We will be given then the mass of water that forms, the mass of carbon dioxide. We'll have to make some assumptions about other elements that might have been present in our sample, but we can do an example to illustrate what we're talking about here. So here's a very good example then. I have a compound containing carbon, hydrogen, and nitrogen, and that's it. Our 100 milligram sample contains, I don't know what it contains, my apologies. What I do know is that when I react it with oxygen, I produce more carbon dioxide than my original sample had. Well, that's not terribly surprising. Oxygen is much more massive than carbon. And so whatever X is, we've added that much O2 to our sample, increasing its mass quite dramatically. 66.18 milligrams of water. There again, oxygen weighs much more than hydrogen. So although there was hydrogen in my original sample, now it's being converted to water, and we've increased by the atoms of oxygen that are attaching to those hydrogen atoms. And then lastly, we detect 96.74 milligrams of nitrogen dioxide in this form. What is the empirical formula for our compound? Now, an empirical formula derived through an experiment like this may not match the molecular formula of our compound. And I add on a little twist at the end of this problem to illustrate what I'm talking about. Organizing our data, always a good idea. We're going to do that organization in the following way. I'm taking my combustion example, created a little spreadsheet here. I've written the data up here, just copied and pasted so that we wouldn't be confused as to what the heck I'm talking about. So the first compound that mentioned is carbon dioxide. This is coming from our analysis. Water, nitrogen dioxide, these are found in water. Now I want to point out that there's 1 carbon per carbon dioxide and there was 1 nitrogen per nitrogen dioxide, but There are 2 hydrogens in water. So we're going to have to multiply by 2 the results that we're obtaining in this fashion. I'll try to amplify on what I just said as we go. But let's take a look at what I have. Taking the data as stated in the problem, I put the molar masses. This is the molar mass of CO2, not the atomic weight of carbon. It's CO2 that our combustion analysis gives us. This is the molar mass of water, although I think it should be 18.02. It does not impact our results by putting that 18.01 there. And nitrogen dioxide I calculate to be 46.07 grams per mole. This now is going to tell me the moles of carbon dioxide molecules, water vapor molecules, nitrogen dioxide molecules. But I want moles of atoms. So the result here is going to be the same because carbon appears just once in carbon dioxide. Here the same because nitrogen appears just once. But when I go to do this, I have half the number of hydrogen atoms, moles at a time, that were present in my 100 milligram sample. So I have to multiply by 2. Whoa. When I take that result, 66.18, divide by 18, I get something like 3.12, something like that. That's where I multiplied by 2. I have to multiply by 2 the number of moles of water to get the number of moles of hydrogen. So what have I done here? I've calculated the, since it was milligrams here, these are the millimoles of atoms that were present. Milli is simply 1/1000. And so I have 5.245 millimoles of carbon atoms, 7 millimoles of hydrogen atoms, and 2.1 millimoles of nitrogen atoms in my 100 milligram sample. What did I do here? I took the number 2.1, it being the smallest, and divided it into each of these. I can't simply round these off. So when I do that division, I get 1 because I'm dividing the smallest by itself. I get 3.5, I get 2.5. This ratio is getting closer to the empirical formula. However, it needs to be whole numbers. So our empirical formula now works out to be C5, H7, C5, H7, O2. And unfortunately, Zoom won't let me do subscripts there. Okay. Now, the twist on this problem. Through separate measurements, we find that our C5, H7, and 2 weighs something in the range of 180 to 210. When you work out C5, H7, and 2, you will not get a molar mass between these two numbers. So we need some whole number to multiply all of these numbers by to bring us into a molar mass. That is to say the mass of the molecule itself. It has to be in the range between 180 and 210 grams per mole. We will work that one out in class. Now the homework, this was last night's homework. This is what we will be working on in class. And so this is my attempt to what we call flip my classroom. Lectures at home. Let's do some work in class.